Welcome to this explainer. Today, we're stepping into the absolutely fascinating, high-stakes world of molecular chemistry. But hey, we aren't just looking at boring beakers and lab coats here. We're going to look at this like a giant, microscopic detective story. Imagine trying to identify a suspect you literally can't even see with a microscope. Well, that is the everyday reality for chemists. They have to piece together these entirely invisible clues to figure out what exactly they're working with. And as we'll see today, artificial intelligence is finally stepping in to help solve some of chemistry's most stubborn, invisible mysteries.
Okay, let's dive into why getting a molecular structure exactly right is so incredibly important, and why the stakes are just so high. On one hand, you have glucose, the everyday energy your body runs on. On the other hand, you have fructose. Now here's the crazy part. These two molecules actually share the exact same chemical formula. But if you just reroute a handful of those unseen bonds, it completely changes how the molecule acts in our bodies, sending it down an entirely different metabolic pathway.
And honestly, this brilliantly illustrates the real danger in this line of work. Sometimes you don't even need to reroute bonds. Simply flipping a molecule into its exact identical mirror image can trigger an absolute disaster. History showed us this the hard way with the thalidomide tragedy, where a completely harmless, helpful sedative, when flipped into its mirror image, tragically became a dangerous teratogen that caused severe birth defects. So identifying molecules isn't just some abstract academic exercise, right? It's literally a matter of safety and survival.
So you might be wondering, just how big is this microscopic lineup of suspects? Well, take a look at this. The CAS registry is the world's largest chemistry database, and it currently holds over 290 million disclosed substances. 290 million! Chemists are constantly having to translate between hand-drawn structures, these massive databases, and really complex instrument readouts. It is an immense, frankly overwhelming scale, and keeping up with translating all these structures manually, it's practically impossible.
To make matters even more intense, look at this number right here. 15,000. That is roughly the number of brand new chemical substances discovered every single day. Every single day. This is the grueling daily grind chemists face. With 15,000 new invisible structures being added daily, the traditional manual methods of identifying and translating these molecules are creating a massive bottleneck in scientific progress. Section 1. The Interrogation Room. Reading molecules with magnets. Since molecules are way too small for standard microscopes, chemists actually have to see these invisible suspects using a canonical interrogation technique called NMR spectroscopy. It's essentially a clever way of reading molecules using incredibly powerful magnets and radio waves. Let's walk through it together. First, you dissolve your unknown sample in a liquid solvent. Second, you probe that liquid with magnetic fields and pulses of light and energy. Third, depending on the exact shape of the molecule, it absorbs and deflects that energy in really unique ways, which the machine then records as an energy spectrum. Finally, the chemist gets a printout of jagged peaks, and they have to match those peaks back to specific atoms to reveal the molecule's hidden shape. But here is the catch, and it's a big one. Chemists must manually match every single peak on that readout to an atom by hand. This matching process is incredibly tedious. In fact, it's widely considered one of the most time-consuming steps in all of synthetic chemistry. Imagine getting a massive, complicated barcode and having to manually calculate what item it belongs to, line by line, peak by peak, for every single new compound you make in the lab. Section 2. The new detective in town. AI enters the lab. So, researchers at Anthropic are testing how their AI model, Claude, can act as a master linguist and translator for these complex readouts. Instead of a human spending hours translating those jagged instrument peaks, Claude can read them and instantly translate them into structured, understandable reports. Now, what's really interesting here is how Claude actually stacks up against industry standards for predicting hydrogen peaks. Claude Opus 4.7 actually beats 30-year-old dedicated chemistry software, achieving a surprisingly tiny margin of error, just 0.079 parts per million. Essentially, it's placing the peaks almost exactly where they need to be. And it goes way beyond just finding the general position of the peak. Claude was incredibly accurate at predicting the complex shapes and spacing of those peaks too. In fact, Claude accurately predicted the sub-peak spacing roughly 80% of the time. Compare that to the classical, dedicated software tools, which only got it right about 26 to 35% of the time. The AI isn't just keeping pace with the old tools, it is heavily outperforming them on the really fine details.
Okay, so everything we just talked about was forward prediction. Giving the AI a known structure and asking, hey, what would the resulting graph look like? So we know for sure it can predict a graph from a structure. But what if we work the problem in reverse? How might a researcher use Claude to identify a completely unknown molecule from just a confusing spectrum graph? This is called inverse prediction, and it's by far the hardest task in the lab.
Well, here's a walkthrough of how a modern researcher can now effortlessly use AI for this exact task. You just grab your basic 1D peak list, which is honestly just a text document listing those jagged lines, along with the basic chemical formula of the molecule. Then you literally just paste that text data directly into a chat window with Claude. That's it. You entirely bypass the need for highly complex, expensive 2D NMR software that requires specialized training to even operate. Within moments, you receive instant, ranked structural candidates right there in the chat. It's a real game changer. And when put to the test, Claude correctly recovered 8 out of 8 of the simpler molecular structures on every single attempt. It did this using only the basic spectra and formula without any extra hints at all. So the crucial point here is that Claude acts as a brilliant, flawless digital forensic analyst, easily deducing the chemical structures perfectly on these simpler targets, stuff that usually requires tedious human effort to uncover.
Section 3. The cold cases, where Claude still struggles.
Now, while the AI is deeply impressive on simpler molecules, we definitely need to ground this a bit. It is not a magic wand just yet, and highly trained human expertise remains entirely necessary. Here is a quick breakdown of the current limitations. For very dense, tangled, fused molecular rings, Claude still needs hints about what the starting materials were to get it right. It also has limited solvent coverage right now. For instance, it's untested on specific solvents like methanol D4. Advanced multi-step 2D experiments, things chemists call COSI or HSQC, are currently out of scope. And finally, it just cannot untangle massive, complex natural products yet. Basically, the more complicated and unusual the molecule, the more the AI still needs a human's guiding hand. But let's zoom out and look at the big picture and our core takeaway for this explainer. As Anthropic notes, Claude is starting to meaningfully assist chemists with the daily translation, recall, and integration work. While it's absolutely not perfect and can't solve every complex natural product out there, AI is finally here to lift that massive, exhausting burden of manual translation and peak matching right off the chemist's shoulders. Which leaves us with a truly exciting, provocative prospect to end on. What happens to the future of science when those 15,000 new invisible molecules discovered every single day are suddenly understood in seconds rather than hours? We are looking at a massive, rapid acceleration of chemical discovery. New medicines, new materials, and new solutions to global problems are about to be unlocked faster than ever before. Thank you so much for joining me on this explainer, and I hope you're leaving just as curious about our incredible microscopic world as I am.